Okay, here we are, first video of the semester. And I try and keep my videos under 25 minutes because I want to use the other 25 minutes of class to discuss the videos and get a handle on what actually happened during the video, and then you have the video to go back to if you need to. I'm also thinking about posting these notes separately as a hard copy and see if that works as well to help with retention. And so when I make videos, I always number them like this. And I'm going to call this one video 0. And this is the 4th of February, 2021, I believe, if my computations are correct. And what I want to do is give a brief introduction. To calculus. Now, I hijacked this idea from the Khan Academy, which I'm a huge fan of. I learned how to make videos and what software to use and things like that from Saul Khan and his academy. Sometimes his videos don't align with what we're doing, and so I don't like them. But most of the time I do. And so this is a video based on what he did with his intro, with a little tweak and a different notation because of the way the course runs. All right, so let's get into this. So calculus, was invented or discovered, depending on how you feel, in the late 17th century. And it was founded by two people working separately. Isaac Newton, who's British, or was British. He was famous for the apple falling in the tree and all that. And Gottfried Leibniz, depending on how you say that, who was German. He's from Germany. And I don't know, we can't say what was going on then in the late 1600s, but apparently Isaac Newton figured this all out first, but Leibniz was the first to publish the results. And like any good controversy, people said that he plagiarized Newton and blah, blah, blah. But they use different notations, and I think, from what I've heard, the notation that most calc books use, that we use, comes more from Leibniz than it does from Newton. So we have them both to thank for this. And a lot of people, especially when you have this spring semester Calc 1, are MET, FET students, and they wind up taking Calc 2 as well. And for you people, you really need to think of Calc 1 and Calc 2 as one long course, because it's quite difficult, and you need everything from Calc 1 for Calc 2. So keep that in mind as you're going through the semester, that none of this stuff is going away. In fact, it gets harder. And in Calc 1, it's called differential calculus. And Calc 2 is I'm forgetting the word now. Integral calculus. Duh. And differentiation and integration are the two major words in calculus, and they undo each other. And so for this course, we're working with differential calculus. And so, all right, what were Newton and Leibniz thinking about when they did their thing back in the late 17th century? So we're gonna follow Saul's lead here and talk about the 100-meter dash. And so the world record, the 100-meter dash, happened in the Olympic trials in 1988. This was the female, so the female world record. And it was set by a woman named Florence Griffith Joyner, or as the world knew her, FloJo. She was super cool, clearly very strong and fast, and she ran the 100-meter dash in the 1988 Olympic trials in 10.49 seconds. And I like to talk about this because the male record gets beaten every other year. It just keeps getting faster and faster and faster, and it's currently held by Usain Bolt. I think you ran a 9.58. But this was huge, and it's stood the test of time. 88, 98, 2008, 2000. It's 33 years old, and so it's pretty incredible. And we're going to sort of link FloJo with this idea of the differential that was brought to us by Isaac Newton and Leibniz, and just have a little fun with it. So let's take a look at this 100-meter dash in math terms. Okay. So we're gonna draw a graph here, and we're gonna label our graph as usual with an x coordinate and a y coordinate, and so y is going to be distance ran. That's our dependent variable because it depends on how long you run for, and x is going to be time. And time is going to be in seconds, and the distance is going to be in meters. So let's just put this, there's our 100-meter mark, and down here is 10.49 seconds. And if you think about where this goes, up here, that's the point on the graph. Now, what we want to look at first of all is her average speed on the run, or on the dash. Okay. So what do you do? So average speed, it's going to take the distance ran. So whatever this change in distance is, and here's our first calc term. We're going to use this symbol, which is a delta, a Greek delta. It's a little triangle. Delta y, that means the change in y, and in this case, the change in y is 100 meters. Okay. And we put that over how long? The change in x. And in this case, the change in x here is this distance here. That's delta x. Okay. Let me get rid of that extraneous mark there. I don't want to put an equals there because it's already on the. And so this gives us our average speed. You just take the distance traveled divided by how long it took you, and what does this give us? We have, oops, I still have the eraser going there. There we go. We go 100 meters over 10.49 seconds. This gives us units, meters per second, which is speed. And let me do this here. I'm going to get my calculator out. Where is it here? Oh, I did it before. So 100 meters divided by 10.49 seconds, 9.5328, blah, blah, blah. So we're just going to say 9.5. So it's approximately 9.5 meters per second. This is our average speed. Now, if we draw a dashed line here, put it in blue, just thinking back to algebra, delta y over delta x is just change in y over the change in x. It's rise over run. So her average speed, this 9.5 meters per second, is the slope of this dashed line. And that's the concept that Leibniz and Newton exploited to come up with this idea of a differential. which I'll get to in a second here, or over the next weeks to be more correct. But let's just put this 9.5 meters per second in perspective. If you take 9.5, so let's say she could keep this pace for an hour. So you take 9.5, let me do some math here on the calculator. So if you take, clear all, if you take 9.5 and you multiply it by, clear all, 9.5. If you take this and you multiply it by, how many seconds are in an hour? 3,600. It gives you that one, 34,200. And I know from swimming that there's roughly 1,600 meters in a mile. Oops, it doesn't do that. So you take answer divided by 1,600. And it gives us 21.375. So 21, so roughly 21.3 miles per hour. Think about driving a car. I have a speedo on my bicycle, and that's incredibly fast. Okay, so the average speed here is 9.5 meters per second, or 21.3 miles per hour that she's running. But we know from watching a 100-meter race, and this assumes that you can't start at 9.5 meters per second. You start at 0 meters per second, and you accelerate to 9.5. And in the case of any of these races, 9.5 is not necessarily, well, it can't be your max speed. So at some point, you're actually going faster than that. And so we can think about what her race actually looks like. Let me get a different color in here. Let's get some purple. Purple is my favorite color. So if we really want to sort of model her race along here, she starts here at 0, 0, 0, takes off, and then accelerates. So she's going to go faster than 9.5 meters per second, and then probably level out, and then maybe get a little tired at the end and come back this way. Okay, and so what we want to know, what Leibniz and Newton want to know, what Flojo probably wanted to know was, how fast is she going right now, like at this point, or at this point, or at this point? The average speed doesn't mean as much as, for example, what's the max speed? And what we do, again, is we exploit this idea of the right triangle. Okay, so let's just pick this point here that I'm trying to make big so you can follow along and say, how fast is she going right there? All right, I'm going to go back to red here. It's a different color, not a different width. So if I made a little triangle right here and connected this point along the graph and this point along the graph and made a line here between the two, the slope of that line, so this would have a little delta x, and that would be a little delta y. This is a right triangle. With this much smaller triangle, that line, the hypotenuse of that triangle, so go back here. So the hypotenuse of this little triangle approximates the speed. It's a little tiny little average, like let's say delta x. Let's say delta x was 0.001 seconds. So it's a tiny subset of the 10.49 seconds. And if you made the triangle along the curve there, this little delta x would be 0.001. I'm not sure what y would be. It would be some number. And the curve itself would not be exactly on the line, but it would be really close because we've made this triangle so small. And for this little instant, this 0.001 second, we would be able to get the average speed over this 0.001 second time interval. And that would be a really close approximation to her speed right here at this point, which corresponds to this big purple point here. But it wouldn't quite be exact. And so here's the big idea. I'm going to take this triangle and make it huge. Same triangle, same one. Now we've taken an electron microscope and magnified this thing out. So this is 0.001. Again, we're not sure what y is. And the curve itself, because we've now magnified it even further, would probably be something like this, maybe. I don't know. But the slope of this line, which has a name, it's a secant line. And again, I'll make this all rigorous in the next days, would be a good approximation to the speed at this point, which again corresponds to the speed at this point. And so here's what Leibniz and Newton did in all their genius. They said the average speed is delta y over delta x. Okay? And what you want to do is you want this delta x to get smaller and smaller and smaller. And in the language of calculus, what we say is we let delta x approach 0. And as it does, the average speed becomes the speed at the point. And when I say point, I mean this point right here. And it's your actual speed at that moment. Okay, and this is called instantaneous rate of change. And that's the key word of this course. If I ask you what a derivative is, you say it's instantaneous rate of change. And it doesn't have to be speed. The other example I was going to use for this little introduction was a road. And you know how when you're driving, I guess you're all driving, and you get to some road. The example I had was called Slumgullion Pass. I went to school in Colorado, and this is the steepest road in Colorado that's paved. Slumgullion Pass. It's down in southwest Colorado, and it has a 9% grade. And so it's the same idea. You have a delta x here, which is in feet, and a delta y here, which is also in feet. And then the slope of this line is the grade. So in this case, it's going to be 9 over 100. And so if you have 9 feet over 100 feet, they cancel and you get 9%. I didn't like this example as much, but I was just pointing it out that this idea works with a lot of things. We can do it with money, profits, and loss of profits. We can do it with engineering applications and population growth and all this kind of stuff. And so this idea of instantaneous rate of change is really, really, really what we're talking about this semester. What's happening right now? Okay, and so not putting too much calculus into this because I just wanted to give a little taste for these triangles and remind you that calculus is just an application of algebra and trigonometry. That's all it is. And it's super fun if you take the time to really put your mind into it, and if you have a little bit of intellectual curiosity, because this stuff is fun, even if sometimes it can be what you might call frustrating. So anyways, that's a little intro to calculus and rates of change, instantaneous rates of change. And I got to talk about one of my favorite past athletes, FloJo, who sadly passed away at a pretty young age. I think she was in her 40s. I'm not sure how she died, but she still holds the world record, and she's the fastest female who's ever lived. Okay, I'll see you all in a few minutes.